Welcome everyone to the second part of this series. In this part, we will build a level 1 self-driving car and we will automate one task, which is the cruise control or speed control. We'll also get to know the PID controllers. They are classical control systems that are widely used in self-driving cars. So we'll also get to learn them today and how to implement them in Unreal game engine. Self-driving cars contains many subsystems. Controllers, basically they represent part of them. Uh, PID controller is an example of these controllers. Now, controllers in general, they need a reference or they need a target that they would control the vehicle to follow that target or that reference. So the controller cannot operate without target, and this target or reference usually is coming from motion planning. Motion planning, as we see in the picture, basically is the planned path and acceleration and speed of the vehicle that it needs to take. So the motion planning itself, in order to do that planning, it needs an understanding of its environment. It needs to know if there are some vehicles, for example, in front of me, if there is traffic light, if there is an obstacles, if there is an intersection. So the motion planning needs what is called the perception of your environment. And perception is, as I said, object detection, is mapping and localization of your environment. We'll also come to do that in this tutorials. But the perception itself, which is a set of algorithms, and now mainly machine learning or deep learning algorithms, needs input from sensors. And we have different sensors that are used in self-driving cars, like the vision-based sensors, which is cameras. We have location like GPS. We have LiDAR for 3D construction. We have radar also. So this is basically the process, starting from sensors to perception to motion planning to controllers. Now, in this tutorials, I'll actually start from the controller because it's the simplest one there. And I'll assume that the path is already planned. And today, as I said, we will cover now the speed control. And there we need to follow the speed profile or the speed reference. So our target today, as I said, is the PID controllers. So just to understand how the control system works and what do we mean by the controller and what do we mean by reference and what is the error. Let's assume I am the controller or yourself as a human is the normal or the conventional controller of cars in general. So I have a target which, let's say, is 30 kilometers per hour. So this is my target speed that I need to drive at. So let's say we are driving in 30 zone. And of course, I want to now reach that speed first. So I need to give thrust, which is means like I need to give force to my car in order to move toward that speed. And first of all, my speed would be, you need to remember this, proportional to the force that I am giving this car. So if I now increase my force, first of all, we see that the red here is my speed now. And I'm trying to actually drive at the reference speed as you saw. What I'm doing is I'm increasing the force in order to cross that line, reference line. When I cross it, I will actually move my hand out. So I basically reduce the speed again. And if I am control, you see it is hard here to stay at a steady state, what is called, which means where it converges at the target speed. Of course, in now advanced cars, modern cars, it's not that hard for your driver to drive at steady speed. But here I'm just showing you an example in this game environment that it is hard. And I'm showing you basically that also that the speed is proportional to the force that I am giving this car. So this is basically the general architecture of control systems, which has two subsystems, let's say the controller and the plant. The controller is actually us, what we were doing now when it comes to controlling the speed of the vehicle. The actions here, actually the output of our controlling, which is the thrust force or the throttle that we are giving the car. And the plant is the model of that car. So the model, which means it takes an input, the thrust or the throttle, and it's basically generate the speed of the car. So in this simulated car that we that we are using in our simulation, basically the plant is already modeled. So we have a mathematical model, mainly differential equations that basically model the relationship between the throttle and the speed as an output. Usually, if you are building a car from scratch, let's say, then you want to automate this car, then you have to build a mathematical model that that relate or that model the relation between throttle and response. Now, this is basically assume that we have the plant in this case, and what we will focus on the basically on the controller. It is similar to if you are from the reinforcement learning area. It's similar to what is called model-free reinforcement learning or model-based reinforcement learning. So here we are assuming that we have model-free because the plant is already designed for us. Now the controller, as what we have basically will be what we have been doing when I was driving, actually, or what I was doing. So it's basically controlling the action, which is the throttle. So I'm giving more throttle to increase the speed. Then when I basically overshoot or cross the target speed, I will remove my hand, as I said, away to reduce the speed again. So these are my actions. The response here, as you see, basically is we have a feedback loop, and this is also the speed. So I was looking at the speed and my speed, my current speed, and I was always basically comparing the target speed with my speed. So at the beginning, for example, the error, which is the difference between the reference and the actual speed, was 30 kilometer per hour because the car was steady, it was stable and stopped. So when I increase then my action, or when I increase the throttle there, the car started to accelerate and the error started to decrease until it reached zero. But also, as I said, it was hard to keep it at zero, so we were actually oscillating around the target speed. So the controller role is to do actions that would lead the response signal actually to converge at the target response or signal value. So we'll talk about one type of control system, which is one of the most common actually control system because it's simple, it's easy to interpret it, and also it's easy to check for stability of the system. And PID controller, it is this one, as I said, and it stands for proportional, integral, and derivative controller. We'll talk about the three parts. But before that, let's talk about the car model. As I said, we have the thrust force. This is barely the force that is the output of the controller. And we have the dragging force. Of course, you should know this from physics. If the thrust force is equal to the dragging force, or equal or actually lower than dragging force, then the car would not move. And in order this car to start moving, we need to have thrust force basically bigger than the dragging force. Just remember this because this would be important now for the next steps in the modeling of the controller. Just to make it more simple for you, if we talk about now control, let's take a simple example, which is the control of temperature. Let's assume we have this valve here on the right side, and this valve is actually the control action, which is how much I would open this valve. And the more we open this valve, the more hot air would actually go through this valve to the room. Let's say if we are controlling the temperature of a room. And the more hot air, as I said, the higher the temperature would be. So the temperature is proportional to, or actually the error temperature is proportional also to the amount or the density of the hot air. Uh, our reference here, basically, we have the plant, which is the model that basically takes the, for example, the valve, how much the valve has been opened, and the response is the temperature. This is the plant, which is the model of that. We need here basically the sensor that is measuring the current temperature of the room and sending this current temperature of the room as a feedback loop to the controller. So the controller would basically try to open more and more the valve in order for the temperature to reach the target temperature, let's say 20 degree. And if I increase this temperature again, the controller would open more. If I decrease it, basically the controller will start to close that valve in order also to decrease the temperature. So this is the role of controller. And this is basically what first means the proportional controller, because as I said, the error is proportional to the actions that we are giving the plant. So the more the hot air, the higher the temperature, and so on. And this is the proportional part of the PID controller. So we have here the action UT, which is T stands for the time, of course, and U here is the action to the output of the controller. We have what is called the gain, and here the proportional gain K. We'll see what the effect of that gain multiplied by the error. If the error is 0, then we should get high action. So if my speed is 0, then I would give basically high throttle or high thrust force in order to increase the speed. The closer I get to the target speed, the lower the error is, and the lower the action that I need to give, or the force that I need to give that vehicle. So this is the idea of the P part, or the proportional part of PID controller, which in some systems it's enough. So you don't need the ID, which is you don't need the integral and derivative. But the P part alone usually, especially when it comes to robotics and cars and drones, is not enough because of what I actually just showed you, the thrust and drag force issue. So let's try actually now as a first example, let's try to implement the proportional controller alone for our car, and then check what's wrong with proportional control, why it's not enough and why it's some cases not stable. So in the previous session or part, we stopped here where we added the speed error there just to see how far we are from the target speed, which is 30 km per hour. And if I press on moving forward, the speed would increase. Then I have to depress, for example, to reduce the speed and so on. And this is how we control manually the speed. What I want first to add is basically another text visualization where we actually want to visualize now the throttle force, because I want to actually measure what is the minimum throttle force that would lead this vehicle to move, which should be, as I said, for example, the throttle force would actually lead to a thrust force, which actually should be bigger than the dragging force. So what I want to do now is basically, as I say, to add this additional text. And if you remember, first of all, we need to add here another U property as an F text. And so we had the speed display, we have the speed display or the speed error display. And here I would add the auto display string, and that is under the header of our main pawn. If we now move to this tab, so what is basically the default throttle that this car is taking when I press over the move arrow, which is the up arrow here, or W. If we want to check that, you can go to project settings here, and then we have the input under engine, and we see that they are predefined for this game, actually predefined bindings. So we have the access mappings and the action mappings. So the access is more like a continuous input, like it is not an event. It's more like for example, controlling the forward and move right or move left. So we have basically access control there. And if we have an action like events, basically like, I don't know, for example, handbrake is an event. So to just, when you press that, it will trigger the handbrake. But if, for example, when it comes to move forward and I press moving forward, which here we can see the keyboard buttons that are responsible of moving forward. We have WS, up or down. And W, when I press W, basically it would consider here the value 1 that I put it under scale. And this value 1 actually is a throttle value. And here it's fixed. We cannot control it. If we want actually to change it, we need to change the settings. So we can probably control it within the game. And I will show you like a way around that, how we can control that. So this is basically, if I am moving forward, the throttle would be 1. If I am moving backward, which is basically braking, the throttle would be -1. Up, down, the same. These are if you are using gamepad, and the same for moving right and left. For example, we have also here the steering angles plus or -1 and so on. So when this is triggered, so when I press either W, S, or up or down. So when I press W, first of all, the value would be 1. And if we go back to the code here and search for the input component, so this is basically what is responsible of the input actions. And basically, this is a function here. It's called setup player input component. And you see there we have kind of listeners. And here it is called player input component. Here's basically the function, which is called binding access. This is the event name that we define here. So if we look here, we have basically the event name. So I'll move forward. And this is basically that this is representing here the pawn. And this is the response, which is received. Basically, we have a reference here to a local function that when this event is triggered, we would need to call this function, which is called the move forward function. And if we search for that move forward function, basically it is here. As you see, it takes a value, and this is the value of the scale that we have defined. So it would be in this case either +1 or -1, and that would be the throttle value. Okay, and so what we want to do is basically want to control this value, as I said. So I will add here another parameter. I would call it. It is actually float scale category control. It should be, we can edit anywhere. So we here actually can write, I'm not sure if it is not here. Yes, control. Blueprint read only. So that should be okay now. So because we want to change it now only within C++, so I don't want to change it within Blueprint. But if you are wondering what this edit anywhere and blueprint, you can check the documentation of your property. So next step is basically we need to manipulate this one, and first we need to give it an initial value. So we have what is called the begin event. So this basically whenever the game starts or the simulation starts, this function would be called. So all the initial values you can define them here. So I want to actually give that value of 0.1. Now we go back again to move forward here. So we have, let's call it, but this should be, and we send the new value or the scaled value to the throttle. And also I need to control this one. So I want to increase it or decrease it just to see what is the minimum, as I said, the throttle value that would move the car. So to do that, we need to create a new event here, which could be event or scale, but or access, but I will just make it an event. So here we have the action mapping. Let's put here increase the throttle scale, and I would select just random. So let's say T, but this isn't. You can select whatever you like. So for example, and here I want to decrease the scale, and keywords, let's select Z. So we need to copy that. First save here. And now we go back to the C++ code here, just to keep a track of that. So what we need actually to bind action, it's not an access, and the name of the action is increase its scale. And here basically we need to define a function for that. So let's call it same. If we define function, actually we need also to define the function here in the header. So you can see the move right and move forward functions and other reactions. So we need to define this function here as well. So we have void increase scale, doesn't take any value, and also one for decrease. Just want to make sure that the decrease name is correct. Okay, so now we have defined this function. We need to now define the body of that function. So let's copy these two. And here we have increase. So what I want to increase, actually, I want to increase the throttle scale here. So let's put like this. So I would add 0.1. And when I want to decrease 0.1. So we need also to bind that action. Okay, so the last part is now we need to visualize the scale value. And to do that, if you remember basically what you have done here, so we need to have a display string there. I would keep it as an integer, so because it's a float, so as a number, sorry, as a float. So we want to actually take the throttle scale and this our to make sure it's correct. And here you have to call it display string, which should be basically the same as that. But yeah. Okay, so it's not kilometer per hour, so let's keep it like this. And okay, so what else? Yeah, so here now we just need to add one more display. Again, it is the throttle speed here, so that is okay. This one and then this one. No, sorry. Yeah, so here let's give it a different name. Then we put that here. Can keep the color red. I would maybe lights here, but now, yeah, so 150, so let's, that should be fine now. We need to compile. We did many changes, that's why it takes a while. Okay, we have an error. We forgot semicolon, seems. Here it's fine. Here it's fine. Here. Okay, so let's try again. Another error. Okay, we have seems to definition of oh no. Again. $229. Oops. So after the compile is completed, basically we can now press play, and we see now we have 0.1 the throttle here value. And if I want to move my car by pressing move forward, you see it can't move because the thrust force is lower than the dragging force in this case. So if I increase now the scale of the throttle value to 0.2, doesn't move, or actually is moving slowly. 0.3 is better, 0.4 of course better, and so on. So at the minimum, basically throttle value that can lead the vehicle to move is actually 0.2 is very hard, but 0.3. And we need to remember that. And let's try actually, because the dragging force, of course, here at the hill is higher. So if I decrease the dragging force 2, it won't move 3. Also, no. Yes, 3 is almost fine. 4. So between 3 and 4 is the minimum dragging force. We need to remember that, as I said now, for the modeling of the proportional controller. Before we start modeling the P controller, which is a proportional controller, I want to add the time series plots to our game scene so we can see how the controller is doing. And also we need to, so this time series basically plot which shows the target speed, the actual speed of the vehicle, and also would show us the throttle time series, so the force that actually the controller is giving the vehicles, which is mean the actions of that controller. And in order to be able to plot that time series, there is a package that is free. It's called Kantan charts. So if you want to find it, you should actually go here to the marketplace, then search for chart, and you would see it here. So it's called Kantan charts. Okay, for some reason but basically this is basically the Kanban chart that you would find it under the marketplace. You can install it to your engine. So we're using 4.23, so that's possible. It works with cross platforms, Windows and Mac or Android and so on. And if you have installed this to your engine, then when you start your game, you can actually find it under settings, plugins. Then here we have under actually installed. So we have basically different plugins here, but here we have, for example, under installed, and I want to enable these charts. So press enable, and you need to restart your game. Okay, so what we need to add now is a widget. So let's go here, or one blueprints. Then let's add under user interface, because it would be as a user interface. And here we have widget blueprint. So I would select that. Let's call it time series plot. And here on the basically, this is the region of interest. This is what basically would be the main window or the player field of view. And here we have the content chart. So I would select time series plot. So you need to drag it here. And this is what's called the anchor, and the basically the most recommended step is basically just to scale this anchor from the beginning till the end, so it would always actually adopt the visualization or the time series here with respect to your resolution, and also how big basically, or the window size of the game. So I want to put that graph here. I would call that first is the speed. Now let's call it the target speed plot. It has the lower bound value for the y-axis is actually 0. We don't have speed lower than 0. The upper bound, I would put it, let's put 60 or 70 is fine. we need to, okay, so the next step now is we need to add the graph, which is basically the graphical program of that plot. And first we need to get a reference here. Then we have the constructor, which would be called at the beginning of the game or when we construct this visualization. So here, what I want to call add series with ID. We have here simple Cartesian data source. We have target is Cartesian plot. Target is time series plot. So we need to add series with ID, where our target is a time series with ID. All right. So the target is our target speed plot. ID, let's call it speed plot. And this is the ID of that plot. And then here we also need to give it a name if you want. Speed plot or speed time series. Enabled, do you have lines or only points? I would show both. We have lines and point. So now we need to actually read the speed of the vehicle. And to do that, we need first to have a public variable that represents the speed, and we can access it from the blueprint. So under the car pawn here, I would add something called the actual speed. And here we have edit anywhere, a blueprint read and write, so we can actually read and write it there. So here, when we had the kilometer per hour, so remember this was our actual speed. So let's put that. Then actually this part is not that important, the arrow there, because they are member of this class, but just for you to know what is the parent of that actual speed. And here it should be now actually save. Now if we move back to our game here, again compile so we can see it. Compiling is done now. We can double click here and go to graph, and what we want to add now is basically a reference to our main player. And here we need to write first of all get owning player pawn. So this is the main player pawn class. Then a child of that class actually is our car one or self-driving car one pawn. So we need to cast to that. Cast to self-driving car pawn class 1. Now the target speed that we have defined is actually child of this class, so the actual speed, sorry. So if we here write get actual speed, we can get it. And this should be executed after we add the time series. Now this is basically the constructor. Now at each event tick, which is a counter actually that would actually be triggered at every millisecond or maybe less, depends on your game. But here, now what we want to add actually, we need to add data now. So which means we need to add a data point now. The target is again is this target speed plot. the ID where we want to add this point. Actually, we need to add at this speed plot. And here we have the value. This value actually is the actual speed value. We compile, save, nothing wrong, it's okay. Close this window. Now one more step is basically we need to add now this widget to the game. So we need to go to blueprints, open level blueprint there. Here now we need to first of all get player control. Then here we need to create widget. Then here select our time series as a target. We need to add this to the viewport. And that should be at the beginning of the game. If we compile, save, go back, play. Yeah, so now we have basically, we see the time series of the speed on the left side. I need to increase the dragging again, and now we can see that the speeds start to increase. So what next is basically we need to add also the plot of the reference speed. So if we go back here, we need to add also a global, not a global, but a public variable, call it the target speed. So we have the target speed, yeah, and now this target speed actually, in our case, let's have it now fixed. So when we have the starting of the game, which is under begin, out, it is actually 30 kilometer per hour. So now we need to compile. Now basically we need to duplicate this plot. We call it plot 2. And the only thing we need to change here actually is the target speed. We need to replace it here. The actual speed, we need to replace it with the target speed. And then connect it to the value. Save, compile, save. And of course, we need to add also that in the level. So let's copy this too. Put it here. Now we need time series 2, and the owning player is the same. So, okay, we have the target speed at 30 kilometers per hour, and this is our actual speed that we are trying to drive. So the third order, basically the next plot we need to add, we can duplicate that directly, is the throttle force. So, yeah, let's call it 3. Here, if we go back to the code, I already added actually a variable here, which is a U property again, edit anywhere. It's called throttle force under the header. And basically, I just now want to fix it at 1 because this would be the output of our controller, basically, or the actions of our controller. And so this is just here basically to add it under the actual speed and their update hot setting. And now we need to, I would put it here, or let's keep the same y-axis and just move it along the x-axis. And again, here we need to replace this now with the throttle force. Save, compile. Then again here we need to add it here. So we have here times 3.3. Then same on in player. Oh, before we actually move, we need to change the scale because the scale of throttle is not between 0 and 70. It's actually, I think it's maximum 1, but let's put it at 3. And then play, we see now actually it's fixed at 1. So now there is no, it is not adaptive by the controller, it's fixed at 1. Actually, and now I'm still controlling the vehicle, but now on the right side we see the throttle force. On the left side we see the reference speed versus the actual speed. Perfect. So the next step now is we need to add the proportional controller. And as I said, the proportional controller, the output of that controller, which is the throttle force here, is equal to gain multiplied by the error. So if we go back here to the control part, first of all, we have the move forward event. So this is when I'm pressing up or pressing W, basically, or down or S, basically I'm calling this event. So it's called the move forward, which had the value. Now we added the scale, but now I reset the scale to 1. So basically the value of our axis. Now I would use the same function here, but this function now would be actually taking the value from the controller, not from my input. So first I want to comment this part, so it's not it's manual, it's called now automatic. And if we check the where we stopped there last time, so this is our basically error, and we need to multiply this error by a gain, and that would be our throttle force. So if we check back here the code, so we have basically that error, and here my gain, so the proportional gain, which actually this is would be now selected after some trial and errors, as we'll see later. So I put the proportional gain at 0.1. Then the action is the proportional gain multiplied by the speed error. Now the next step is now we just need to move that vehicle with respect to this action. So that would be UP. And also what I want to do now, I want to remove that from here because now it is actually equal to UP, and that we would see it in the game. So let's compile. Okay, so now the car is basically driving itself. We see that we have the proportional controller. We see that this thrust force is oscillating between, I think, between 0.5 until 1. Now we see also the car speed is oscillating. So what is the reason behind that? If we check here again, so the car would start to increase its speed until it reach actually Let me pause here. So the car would start because we are multiplying the gain with the error. So we are putting a high throat at the beginning. Then this throat would decrease while the error is decreasing until it reaches here, the level. Sorry, I can't see my mouse. So until it reaches here level of 0.3 to 0.4. And if you remember, at this level, the dragging force would be bigger than the throttle force, so the car would actually start to slow down. And the dragging force would push the car to break down. So if we see that, it will actually break down here. And the throttle force would actually, with respect to the error, it would try to increase the speed again in order to get back to the error, or actually the target speed. So if you're using only the proportional controller, we always see this kind of oscillation because it would reach the level where the dragging force is higher than the throttle force or the thrust force, and which would actually decrease the speed, and the gain would, or the controller would try to keep up, so to try to increase the speed. So we would see this kind of oscillation. In order to get rid of this oscillation, basically, this is the role now of the integral and also the derivative we will see later, part of the proportional or the PID controller. But I will conclude now this session here because the second part would be, actually this part is already long, so I would like to divide it to two parts. So now we conclude at the proportional controller, and we'll see in the next video how we build now the integral and derivative controller to have kind of stable and more accurate speed control. Thank you.